Okay, looking at the energy bar charts here, this one's going to be a little bit quick. This is my third attempt on this. Keep recording it, and then my find out that the mic's not picking up for some reason. It's picking up on the others, not this. Getting a little frustrated. So, going to be a little bit quick here. Energy bar charts look at the total initial energy, total final energy, and does are those two equal, or does energy enter or leave our system? Um, Here we say at the beginning, the cart is squished against the spring. It tells us that up here, and we can also see it here. The velocity at the beginning is 0. It tells us that right there. Then the spring is released, pushes the car, goes up at B, at position B. It's obviously got a greater height. The little cartoon squigglies tell us it's moving. The speed at B is greater than 0. They tell us that there. They also tell us up above. So when I look at these energy bar charts, this is really just a way of keeping track of which types of energies are present. So kinetic energy, is kinetic energy present at position A? Well, it tells us the speed at A is 0. If the speed is 0, the velocity is 0. And when I look at kinetic energy, the object must have a velocity that's greater than 0 for there to be kinetic energy. Since the velocity is 0, kinetic energy is 0. So there's no kinetic energy at position A. Gravitational energy at A. Well, for gravitational energy to be present, the object has to have some height greater than 0. It has to have mass, and it's on Earth or some planet. Well, it's on Earth or some planet. There is a mass, but at A, it's as low as it can go. The height is 0. So no kinetic because it's not moving. No gravitational because the height is 0. Elastic energy. So for elastic energy, there needs to be something that's stretchy or compressible. And not only does it have to be present, but it has to be compressed. So if I look at elastic energy, there's a stretchy or compressible thing. Not only does it exist, but is it stretchy or compressible? That is true in this case. This spring is compressed. So just as a record keeping thing right now, just to make sure I remember there is elastic, I'm going to put one block right there. I'll change the amount of it in a little bit, but right now I'm just going to put one to make sure I know there's one there. Last type of energy to look at, thermal energy. In the notes, it talks about thermal energy being present if we notice that if like friction is significant, because then there's going to be a change in temperature, or if there are other things that they tell us that imply that. So they might say friction is significant, or they might say the surface is rough, or different things like that. In this case, we've got a car with wheels, and there's nothing to imply that friction is significant, that there's going to be rubbing in thermal temperatures or change in temperatures. So the only type of energy that we have is elastic. With these bar charts, if there's only one type of energy, we're generally going to say, hey, we're going to fill that bugger up. There are ways to actually truly calculate those amounts, but we need to know other things, and we don't have the equation for elastic energy at all anyway. So we're going to default to, if there's one type of energy, make it 4. If there are multiple types of energies, make them add to 4. So 4 is the most total that we will have on either side. So there we go. There's my total initial energy, the initial L for the LOL chart. Then I look at this energy flow diagram. That's really looking at, does energy enter or leave our system? Well, we have this purple, delightful purple box around here shows us that everything is in our system. If everything is in our system, no energy or items can leave or enter the system. And so if everything is in our system, then the total initial energy must equal the total final energy. So I'm just dragging the equals sign in there to say, hey, this 4 must equal the total over here. So over here, we must have a total of 4. So now we'll look at the final L, the bar chart for the total energies or the energies present at the end. Double clicking, dragging her over to the side, and taking a look at position B at the top. Is there kinetic energy? Well, if we go back to our slideshow, remember kinetic energy is present if the velocity is greater than 0. Well, here it tells us the speed at B, the velocity of B is greater than 0. So just as a record keeping thing, I'm going to take and drag one of these buggers over there and say, oops, I just did the wrong thing. There, clicker, grabber, there she goes. So now I'm just putting one box there to make sure that I know that um, there is kinetic energy present at B. We know there's kinetic energy because it's moving. The speed is greater than that. We have little squigglies. Is there gravitational energy at B? We do that. We know that if there's an object, it's on Earth or some planet, and there's a height that's greater than zero. Well, this height definitely greater than zero. So I'm going to take another one and move it over there. So I'm just making notes to myself essentially that those types of energies are present. Elastic energy at position B. Is there elastic energy present? Well, there is a spring present, but when the cart is at position B, the spring is not stretched or compressed. Remember from our definitions with elastic energy or from our evidence, not only does it have to be present, but that stretchy thing must be either stretched or compressed. And if it's not stretched or compressed, then there's no elastic energy. So there's no elastic energy here. And then thermal energy at position B, again, like we said with energy at position A, there would have to be some friction or something significant there that's causing a change in temperature. And there's no indication. They don't tell us that that's significant here. So there's no thermal energy there. So now I know that I have kinetic energy and gravitational energy. Those are the only two types I have. I need to make sure that I have the correct totals here. So just taking a quick look, we said there was 4 bars of elastic energy in the beginning. We said our system is closed and isolated, so the total energy initial must equal total energy final. And so now if we have 4 here, this total must also be 4. If we're doing this and we have numbers for the mass of the cart, for the height of the cart, for the velocity of the cart, then we could simply calculate those values and we would know exactly what we have here. But for what we're doing right here, we're just saying, hey, you know what? I'm accounting. I'm trying to make sure I have the right types of things. So the thing I need to make sure I have is the same is the total at the end equals the total at the beginning. Total at the beginning was 4, so the total at the end must be 4. So I'm going to go through and say, I know I have some of each. I'm just going to say 2 and 2. That ends up adding to 4. That works. In reality, if we're really picky about numbers and we're saying, well, how do I know if it's 3 and 1 or 2 and 2 or 1 and 3? Well, again, we could calculate it if we had the masses, velocities, and heights and things like that. This is a very good record keeping method. If we're trying to get precise numbers, well, then we would do the calculations. So I'm more concerned right now with the totals. So now, when I go back here, I say, hey, 4 bars of elastic energy equal in the beginning, 4 initial bars of elastic energy in the beginning equals 2 bars of kinetic final plus 2 bars of gravitational final. We're done with our energy bar chart. Have a good one. All right. I hope the volume worked on this one.